Hello everyone, welcome to lecture 6 in the course Software Security. In this lecture we will be discussing about the concept of call stack, the process call stack, right? So in the previous lecture a quick recap, right? What we studied in the previous yesterday's lecture was we looked at the various instructions that are specific with respect to x86 ISA, right? And and we looked at various categories of instructions. One was data manipulation, which consists of instructions like move and all those stuff, right? Move, exchange, and we looked at arithmetic instructions, which were add, subtract, etc. And then logical instructions, which did Boolean operations like AND or XOR, right? And then we looked at compare instruction, and then conditional flow instructions, conditional and unconditional, right? Conditional and unconditional jump instructions, right? So these are the set of instructions that we looked in yesterday's lecture, and we looked at some special instructions like push and the pop, right? And the why it was special, as in it used some and afterwards compare also, right? Why it was special, as in it compare is using an implicit operand, which is the E flags register, which it sets based on the comparison result. And then we have the push and pop instructions, which implicitly use the stack pointer ESP, yeah, assuming it's a 32-bit ISA. It uses the ESP register to refer to the stack memory to the top of the stack, and push or pop an element from the stack and change the value of the stack pointer register, right? And we also looked at what all operands each instruction can take place, uh, each instruction can take, right? So there are like sort of three different types of operands each instruction can operate on. One was register operands. It can be any general purpose register usually, but based on some conditions, um, with respect to each instruction. Some instructions cannot take all of the operands, right? So there are register operands. That is one type of operands. Then you can have memory operands, and the third type is immediate constants. And the difference is, in immediate constants, the value itself is encoded as part of the instruction, whereas in register and memory, the value would be stored in that particular register or in that particular memory address location. And not all instructions support all the operands. Sorry. Sorry for the disturbance. Right. So there are three different operands: register, memory, and immediate. And not all instructions support the same type, all the operands, right? So for example, if we have an immediate operand, if we have the exchange instruction, right? The exchange instruction does not support an immediate operand. And we looked at a reference for the x86 ISA, which consisted of all the instructions, the logic, and what all operands it supports. And we looked at the way the instruction, the machine code format is. So it will have an opcode followed by the details with respect to what operands it supports: operand 1, operand 2. And the opcode basically informs the processor when it executes. When we pass this machine encoded format of the instruction to the physical microprocessor, the processor has the logic within it which checks the opcode and checks whether it's a move instruction or exchange instruction like that, and also the opcode specifies where the operands are placed and which operands the processor should act upon in order to execute this instruction, right? Whether it's a register operand or memory operand or an immediate constant field. Right, so all this information is sort of encoded within the opcode, and it helps the processor to execute the instruction using these operands. So now with this background, let's look at what happens when at runtime, when we want to execute a program. Specifically, we will look at something, a notion called as the process call stack. Right. So a process call stack is comes into the picture whenever we try to execute functions, invoke functions. Like that. So to let's take an example so that it will be better, right? Yeah, it will be easy to understand. So, right. So let's take this example where we have a program. Say, mm, let's have this program. Say int main, right? And let's assume it has three local variables int a, b, and c, and assume a has 5, b has 6, and c has 7. Okay, and now it calls fun1, a function, and passes a, b, c. And let's close this, and let's assume uh, fun1 returns back some variable, and let us place that result in int r equal to fun1. Right, now let's write the logic for fun1. So int fun1, it takes three variables int a, int b, and int c, and the logic is basically it just sums up the operation. Let's assume int sum equal to a plus b plus c, and then it returns the sum. So this is the like a basic code, and let's see what the how the process layout looks like. So assuming this is your virtual memory, right? So this is your lower memory address. So this is the higher memory address. Let's keep it like this. So this is the higher memory address, and this is your lower memory address. And the process layout will look something like this. So at the top you will have something called as a stack region, right? And the stack region will grow downwards. Okay, so it grows downwards. Okay, and then you will have an heap region which grows upwards, right? And followed by that you will have let's just like use a different color. This will be your heap, and followed by that you will have something called as your data segment and decode segment. So this is how your process will look like when it starts when you execute your program and you initiate a process based on this program, right? And say in this function one, you are having some variable um, so let's assume you have an extra statement in between, say int star a equal to malloc of size of int, right? And let's then you return some int star p. Let this be int star p, and you return the sum, right? So basically, when you take a function 1, okay, where will these variables all be stored in memory? So it won't be just like that stored in like arbitrary locations in the memory. Based on where the variable is being declared and based on its usage, the variable, the location where this variable should be stored would be determined by the compiler, right? So for example, if let's just extend the code to assume that we also have some global variable like okay, so let's just assume we have some global variable like int glb equal to 20, right? So basically, let's now see where each of these variables get stored in which particular segment within your process, right? So your global variables get stored in the data segment. Your local variables, basically sum, and afterwards all your local parameters a, b, and c, right? 3, 4, 5. Okay, and then these variables also a, b, and c, right? So 6, 7, 8. Okay, and this variable int r 9. So all these variables get stored in the stack location. So the stack basically has all the variables starting from 1 to 9, sorry, 2 to 9. Okay, and your int star p, right? So int star p equal to malloc. So the whatever you write to the location of p wherever it's pointing to, that gets stored in the heap region. So for example, if p is having some value, say 0x8000, right? The p variable as such should be stored in your stack, and the value whatever p is having is pointing to some address in the heap location. Okay, so this is how your this is how the variables should be stored based on where they are being declared and how they are being used. So in other words, the all the global variables which are having global scope would be stored in the data segment. Your malloc variables, dynamically allocated variables, should be stored in the heap region, and all your local variables and local parameters would be stored in a region known as your stack memory. Okay, and so this is what your the process layout will look like, and all the instructions, right, as in invoking fun1, all those instructions, the addition and everything, would be stored in the code segment. Okay, and this is how the process layout will look like with all the different memory variables stored in the corresponding stack, heap, data segment region. So now let's focus on the stack. Okay, so the stack is not just a region where you store all the local variables, but it also sort of acts like a it supports all your function calls. So it's like a call stack. So let's delve into deeper, right, what really happens in the stack and how it is being used. Right. So if we just take the if we take any stack, the stack memory, right? It basically serves multiple purposes. So the purpose of a stack memory, one purpose is to store your local variables, store all your local variables, and the second purpose is to track your function calls, right? And the third aspect is it acts like a temporary scratch memory. Temporary memory for that active function. So let's look into what this means, right? So when I say we have a code like int, when I say we have a code like int fun1, and it has these local variables int sum, which does something like a plus b plus c, and it takes three parameters a b c, right? So given this, right, now all these variables a b c and sum, they are stored in the stack memory. But where is it exactly stored in the stack memory? And there are multiple questions to be answered, right? So when you look at the previous code, the main function and fun1, there are multiple questions that you need to answer. Question 1 is where are the local variables being stored? As in, specifically in the stack, in what order it's being stored? As in, we have the main functions local variables, and also fun1 functions local variables. Now, where do these local variables are stored in the stack, right? How does the processor or the stack memory, how does it distinguish between main one's local variables and fun one's local variables? Question 2 that we should answer is, how are these parameters passed, right? So you would have learned the concept of call by value, call by reference parameters, right? So here I am passing three integers ABC from main function to fun1 function, means I am passing these ABC parameters. I am sort of copying those values, right? If A has 5, 6 and 7, ABC has those corresponding values. I basically copy those values and make a copy and pass it to fun1, which acts upon those values, computes the sum and stores it in the sum variable. So the parameters passing, how does it pass it between functions? That is that we should understand, right? We have not yet looked into how this happens. It's sort of still unanswered. And the third thing is, when I call a function from main to fun1, right? When main calls fun1, how does the processor know? How does it return back to main? So how does it return back to main? Okay, so uh, when main function calls fun1 function, you do a control flow. You use like a call instruction or a jump instruction, and the control passes to the fun1 function. It executes over there and returns back a value, right? When it returns back a value, the main function takes that value, stores it in the variable r, and does some extra computation. Assume it does some further computation based on that value r. Okay, and how does the processor know how to return back to the main function, especially to this point in the main function? And how does the processor know where to find the result, right? So how do we pass parameters to fun1 function from main function? and how does fun1 pass the result back to main function, and also how does the processor know that after I execute fun1 I should return back to main function, right? So all this is sort of used or solved all these problems via your stack memory. So we look at how the stack memory is crucial to understand all these aspects, right? So we learn something called as the call-in convention. So any ISA or any ISA will have something defined known as the call-in convention. So basically, this call-in convention is something sort of like a standard or a rule which is followed when one function calls another function. And an ISA can support multiple call-in conventions based on which call instruction it's being using, or based on the instructions it uses, or the situation, right? An ISA can support multiple call-in conventions. So here we'll look at the x86 32-bit call-in convention, the standard call-in convention, right? So the call-in convention acts like a set of rules or standard when one function calls another function. So basically, when you use any of your internet protocols, right? Um, the word itself, it's like a protocol. So there are like a set of rules, and say if you want to communicate from one system to another over your internet, there is a set of rules that you should follow, like these many packets it should send via the network, and this the format of the packet, and first it should send the size, then the header of the packet, and all those stuff. So it follows some rules. Okay, so in the same way, uh, one function, when it calls another function and it returns back, it follows something called as a call-in convention, and this is sort of specified by the ISA. And a thing to note is the call-in convention is not sort of like to be strictly followed. The ISA supports multiple call-in conventions. It's up to the program developer, the compiler developer, to choose which call-in convention to use. Okay, so here we'll be looking at specifically the C call-in convention, the C language call-in convention for x86 32-bit ISA, right? Um, so now let's look at the call-in convention for x86 32-bit. So before looking into the call-in convention, we should understand some terminologies. The first terminology is something called as the caller and callee. Okay. So for example, we have in our logic we had a main function which calls fun1, right? So here main function is the caller and the callee is fun1. So caller calls the callee. So main is the caller function and fun1 is the callee function. And the third terminology that you should understand is something called as the stack frame. Okay, so the stack frame is something like you have like in the process layout you have like a contiguous stack memory, right? So this will be contiguous, but this stack memory will be divided into multiple frames. It will be divided into multiple frames, and this will consist of say for example uh, on each function invocation or something, right? So for example, the main function will have say frame 1 attached to it, the main function, and when it calls function 1, right, a new stack frame would be created. Okay, and this will be attached to fun1 function, and when fun1 function returns back to the main function, right? After fun1 executes, this stack frame would be deallocated. This stack frame would be deallocated, and the topmost stack frame would be stack frame 1 allocated to the main function. Now again, when it say main function further calls some function like fun3 means, again a new stack frame would be created. Again a new stack frame would be created, right? On, so in the place of sf2, a new stack frame again sf2 would be created, but this time it will be associated to function 2, function 3, and not function 1. And after function 3 gets executed, after it finishes execution and returns back to the main function, this will also be deallocated. So basically your stack memory is sort of gets divided into multiple frames, and each stack frame gets allocated based on the order in which a function invocation occurs, right? And that's why we term this stack as a call stack basically. So based on the call, the order in which the function calls take place, the stack frames get allocated and deallocated correspondingly. So you might wonder why does the stack frame get allocated? So why can't we just have something like stack frame 1 to main function, stack frame 2 to fun1, other stack frames to that corresponding functions? Why should we keep on adding a stack frame and again deallocating that stack frame, right? So the concept is sort of tied to how we use the local variables. So when we look at uh, say the main function, and if it has local variables, uh, okay, so let's take the example of fun1 itself, right? So fun1 function, let's say it has local variables a, b and c. So these are all local variables in fun1. Okay, and the scope in which these local variables should be active will be within fun1 alone. So whenever the function code with respect to function fun1 is executing, only then will these local variables be active. And if I try to access these variables outside fun1, say within main function or some other function fun3, I cannot access these local variables. So to sort of express this scope, right? Scope of these variables. These local variables are stored in the stack frame corresponding to that specific function's invocation. So whenever I sort of invoke fun1, only then I should access these local variables. And once I return back to fun1, right? You basically would have learned in your C concepts while you're coding your C language, all the local variables would be sort of get deleted. You won't retain the values of these local variables when you return back. So if fun1 is using these local variables A, B, C, say A is having some value like 7, B is 8 and C is 9. When fun1 returns back to the main function, when you again invoke fun1, A still you won't be guaranteed that A will still hold a value 7, B will be holding the value 8 and C will be holding the value 9, right? So these local variables act as temporary variables, and the scope they are active, and that memory is active only when fun1 is executing, and once when fun1 returns back, that memory is lost, right? Those values you cannot go and access, you cannot be guaranteed that those values would be the same, right? So to this concept is directly mapped onto the concept of stack frames. So now the local variables, whatever you are declaring within fun1, say ABC, those will be present, those will be declared in your stack frame 2 ABC whenever the fun1 gets invoked. When a stack frame, when you invoke a function, right, behind the scene, as part of the instructions that your compiler emits, whenever a function gets invoked, it creates a stack frame for that function, and within that stack frame, say I invoke fun1, right? Say I invoke fun1 means it allocates a new stack frame 2 on top of the main function. So remember that my stack frame grows downwards, right? And how the stack works, right? Push and pop. So push is basically on top of the stack and pop removes the element from the top of the stack. So currently this is my top of the stack over here, right? So whenever I invoke a new function, say fun1 or fun2, some function fun1, if I'm invoking, uh, the processor sort of the process, it adds a new stack frame at the top of the stack, and it maps that stack frame to this specific function fun1 which was invoked, which is the callee function, right? And all the local variables a, b and c are placed within this stack frame 2, so it will have some specific address, right? So all those variables will be placed within this stack frame 2's memory range, right? And once after fun1 finishes execution, the stack frame 2 will sort of remove the before returning back to the main function, the fun1 function will sort of delete this stack frame 2, right? As in, it will just like that pop off the stack frame from the stack memory, and now the top of the stack will not be to stack frame 2, but instead it will be pointing to this stack frame 1, right? So this is what happens. This is the concept of stack frames. So whenever you invoke a function, each function is having a corresponding stack frame, and that stack frame contains all the local variables which are being used by that function, okay? And that stack frame is deallocated once that function finishes execution and returns back. And this sort of clearly maps with the idea, with the concept of the local variables, how the scope of local variables is tied to the function's execution, and the scope is lost, the access is lost whenever you return back from that function, right? You don't sort of maintain a history, or you don't store that variable's value in between function invocations. Say when I invoke fun1 once, and again the second time if I invoke, I don't sort of store those values of local variables in the disk and again restore it and use it, right? Those values are lost. That's what local scope, local variables are all about. So the stack frame is sort of a temporary memory space which is allocated and deallocated based on the functions which are getting invoked and returning back, right? So this is the concept of stack frame. Now we looked at the concept of caller, which is the function which is calling is the caller function, and the function which gets invoked is the callee function. And we looked at the concept of stack frame, the high level concept where all your local variables, your stack memory is divided into multiple frames, and each frame can be of some size, it can be of different sizes. So stack frame 1, say your main function is having 8 variables, means it will take up more size. Say it will take up like 8 integers it's having, means each integer is 4 bytes, so it will be taking 32 bytes, right? And say your stack frame 2 is just having 3 integers, then stack frame 2 will take the size 3 into 4, which is 12 bytes, right? So the stack frame, individual stack frames can be of different sizes based on the number of local variables each function is using and other aspects. And whenever a function gets invoked, as part of that invocation, a new stack frame also gets allocated into which that function's local variables are allocated. And once the function returns back to the caller, right, when fun1 returns back to main, the corresponding stack frame of fun1 gets deallocated, and basically you pop off that stack frame, and the top of the stack now corresponds to the caller's stack frame, that is main function stack frame. So this is how the stack frame is maintained in your process at runtime. Okay, and but we didn't look at still a couple of questions are still left unanswered. One, what's the parameter passing, right? So when I tell main calls function 1 and it passes some parameters, how does it pass the parameters? Where will it be passed? Whether it's passed in registers or it's passed in memory or it's passed as constants, or how does it pass from one function to another? That we didn't see. How are the return variables return back, right? That we didn't see. And most importantly, how does my stack know, how does the processor know where to return back? So we mentioned that when a function gets invoked, say main calls fun1, I create a new stack frame, and when fun1 returns back to main, that stack frame for that fun1 function gets deallocated and it returns back to main function. But how does the processor know where to return back in that main function, or more basically, right? Uh, how does it know that the main function is the caller, right? Where does it store this information? So that we'll be looking into next. Right. So to answer the first question, parameters passing, right? Or what to understand parameter passing and return variables, we should sort of first understand uh, what happens really when a function, uh, when main function invokes fun1, what happens behind the scene. So we just saw that a stack frame gets allocated for the fun1's local variables to be allocated, but this allocating of that stack frame, how does it happen, we should see, right? Before that, we saw that each function, so main, when it calls fun1, we saw that say stack frame 1 corresponds to main function, and then we have stack frame 2 which corresponds to fun1 function, right? And say now the currently it's executing in function 1, the instructions in function 1 are executing. Instructions in function 1 are executing. Now we came across two registers as part of our ISA, right, which x86 supports. Specifically, we came across two registers which was EBP and ESP, right? So both these registers, one is called as the frame pointer, okay, and the other is called as the stack pointer, right? So what ESP and EBP is used for is, the ISA specifies, the x86 ISA, that the ESP register points to the top of the stack. So it points to the last stack frame, and your EBP register, the frame pointer, basically is used to access any of the local variables. So your EBP register will be pointing to somewhere over here at the start of the stack frame. So fun1, the function, when it wants to access any of its local variables, right, a, b or c, any of its local variables, it will be using either EBP, the frame pointer, or ESP register to access its local variables and read or write to those local variables. Okay, and when fun1 returns back to the main function, the stack frame gets deallocated, right? And now what happens is, uh, your stack frame gets deallocated, and basically your pointer registers, right, EBP register and ESP register also gets correspondingly changed, right? So now ESP will be pointing to the top of the stack, which is the stack frame 1, and EBP will be pointing to the start of the stack frame 1, right? So based on the stack frame allocation and deallocation, the registers also get correspondingly changed. So your EBP as well as ESP registers change correspondingly based on this, right? And why do we use these registers is that the ISA, so we can the registers are mainly used to track your stack memory, right? So say you have like a long list of functions being called. Say for example you have a call chain where you starting from the main function, it calls function 1, and function 1 calls function 2, and like that it keeps on going calling like nested calls, and it calls like function 100, right? So each time what happens is your each time for each allocation, each invocation of the new function, a new stack frame gets allocated, right, on top of the other, right? If it's like a nested call chain, one within the other, the stack frame gets allocated, so there will be like 100 stack frames, and the currently used active function, so whatever function is being executed, the stack frame corresponding to that function should only be used, that should be the active stack frame. And my EBP register and ESP register will sort of mark the start and end of that stack frame, right? And using those registers, I can easily be able to access all the local variables at sort of like a fixed offset. So for example, say in function 1, my local variables ABC are present in stack frame 2, and say they are present, say stack frame 2 EBP is having some address, say value like 0x1000, and ESP is having a value say 0x 900. Okay, so don't be such a big stack frame usually, but just assume, right? So your stack grows downwards, you should always keep this in mind, right? And now say variable A is present at location 0x 950, okay, and B is present at location 0x 960, and C is present at location 0x 970, right? So given this thing, right, so let's assume okay, let's take this example itself. So your EBP is now pointing to the stack, the beginning of the stack, which is 0x1000 address, and your ESP register points to the end of the stack, 0x900. So when I want to access any variables A, B or C within this stack frame 2 as from function 1, right, I will basically sort of use this EBP register, EBP minus whatever the difference between those two addresses, right? So 0x1000 minus 950, right? So some constant, so some value will be there, some constant value, immediate value. So that will be specified over here. So EBP minus that will basically give the will enable the function 1 to access variable A. So similarly EBP minus some constant value, I can access variable B and C also. So using the EBP register sort of like a fixed register, I can just change this immediate field, the difference field, whatever is being used, to access different local variables which are present in the stack memory, right? So this is an important, so these two registers sort of help the processor to access these local variables, and the advantage of keeping these advantage of the ISA sort of like specifying that these two registers are to required to maintain the active stack frame. So when func1 is executing, the stack frame which is active is stack frame 2, and to point to that active stack frame we need the ESP and EBP registers, right? And both are used sort of like point to the beginning and end of the stack frame 2. And by keeping the start and end of stack frame 2 in these registers, right, you can easily access all the local variables. So assume that we don't have the values of the start and end of the stack frame in the registers. So assume that we don't have something called as the ESP or EBP register. So then what happens is the values where that stack frame is starting or ending for that function will be stored in some memory location, right? Say it is stored in some special memory location. Now to access a local variable A, you should basically first get to know the stack frame location, right? So that is one access, one memory access, and the plus another one is to actually access the local variable present in that stack frame. So it basically means you will be having two memory accesses, and memory accesses are costly because you might have to fetch the contents from the memory and it's not present in your cache or anything. So if those optimizations fail, then the delay will be huge, right? And assume that if this just consider if this to memory access is done for all the local variables, then say you have 100 local variables or something and you're looping through, you have an array of 100 elements, and that array itself is like a local variable treated as a local array, right? So then all your 100 elements would be accessed in this method, right? So this will lead to a huge delay. So storing the start and end of the stack frame in registers sort of simplifies the design, and also you can easily access the local variables within just one memory access. Okay, right. So so we looked at the purpose of EBP register, ESP register. We looked at the concept of stack frame where each stack, the entire stack memory is divided into multiple stack frames. Okay. Any queries you have? Okay. So in that case, let's continue. So we know for a fact that so the registers are sort of so we looked at the ESP EBP registers and the stack frame concept. Now the remaining concept is what really happens, how do we pass the parameters and the return values. So as far as the x86-32 bit ISA is concerned, right? Let me create a new frame. So parameter passing in x86-32 bit ISA. In 32-bit IC, right? So in this parameters are passed via my stack. They are passed via the stack memory, okay? And how it passes is, say for example, I have a main function and it invokes fun1 and it passes three variables a, b, and c. Right now what happens in the stack memory is uh, before the fun1 gets invoked, the execution starts at function 1 fun1. All these variables a, b, and c will be pushed onto the stack memory. So they will be pushed in the stack memory. Okay, so what happens is, say we have uh, this your stack memory, and currently we have a stack frame 1 which is corresponding to the main function. Now when it looks at this fun1, it has to be invoked and I have to pass variables a, b, c. What it will do is it will push the variables onto the stack in the reverse order. So first it will push c, okay, and then it will push b, and then it will push a. So in the reverse order, it will push these three parameters a, b, c onto the stack, and then it will create a new stack frame. Basically, it will invoke function 1. The function 1 will basically create a new stack frame for it to be used. Okay, and you will have something called, then your registers EBP will be pointing to the start of the stack frame 2, and ESP will be pointing to the end of the top of the stack frame 2, as in the end of the stack frame 2, right? And to access all the local variables, you will be basically using something like this, right? So as we mentioned, your local variables will be present within the stack frame 2. Over here your local variables should be present. So over here your local variables should be present, right? So to access all these things, it will be like EBP minus some offset. So to access these oops. So to access these local variables, it will be EBP minus some offset, right? So in the same way, if I want to access these parameters ABC, it will be EBP plus some offset, some immediate offset, or even can be stored in a register. It can be anything, right? So this is how the parameters are passed to from one function to another. Okay, and the way it sort of um, uh, I can pass say 100 parameters also. I can pass 5 parameters. Irrespective of the number of parameters, all those parameters would be pushed onto the stack frame in the opposite order, right? So for example, if we have um, variables a, b, c, d and e, so it will be pushed in the opposite order. So first c, e, d will be pushed, and then c, b and a, right? And accessing the stack local variables, all the parameters are quite similar. Only thing is whether the only thing that would change is the offsets that would be changing. Okay, and so basically the medium of communication between two functions, from one function to another, how these parameters get passed is basically via the stack memory only. Okay, so we looked at parameter passing in, it happens via the stack. Your arguments are pushed onto the stack, but what happens when you how do you return back arguments, right? Return back a value. So in C language, basically any language, right, there will be only like one return value. So you will be returning just not exactly like just one value. So you will be returning some set of values or one value, something like that. So how does this return value get passed from fun1 function to the main function, right? So basically the return value gets your return value gets passed via the RAX register or EAX register, sorry, since it's 32-bit. The EAX register is used as the return value. So for example, my fun1 returns a value, the sum of all the it sums all the variables passed to it, a, b and c, and returns back that sum, and the value of sum is 84, means it doesn't place it on the stack memory for the main function to to read or something. Instead it um, places that value 84 within the register EAX, and once it places the return value on the EAX register, it immediately returns back to the main function. And now the main function, if it knows that fun1 has returned some value, it looks into the EAX register, sees that value 84, and it knows for a fact that that is the return value and uses that value for further computation. So passing parameters from the caller to callee happens via the stack. So you push all the parameters in the reverse direction onto the stack, and uh, returning a value so happens via the EAX register, right? So this is what the x86 bit call-in convention, the standard call-in convention usually is. So this sort of call-in convention, this sort of rule is to be followed between all the functions. So if you take any code, right? So you write some code, you will be using some library. So for example, if you have a some C code, you will be using some external libraries like printf, scanf, or anything, right? You will be invoking those library functions. How do you communicate with those library functions? How do you pass the parameters? So all those functions will sort of be following this call-in convention mostly. Okay, and this is sort of like a standard, and this call-in convention, the specific convention which is to be followed in a particular language, is determined by the compiler engineer. So the compiler engineer sort of specifies um, which uh, uh, as in which variable, in which order the parameters are to be pushed and all those things. So say I can probably write a new language like C minus minus. I can just write like a new language C minus minus, and I can write a compiler for that language where when I invoke a function, instead of pushing it in the reverse direction all the parameters, I can push the values in the exact the way in which it appears itself. So instead of first pushing C, B, and then A, I can push it in the opposite direction like A, B, and C. So it's up to the compiler engineer to decide on the ordering of these parameters in the stack memory, and also the return value. I can use any other register instead of EAX register. I can use any other register also as my return value. So I can use register like EBX to pass the um, return value back to the main function from fun1. So this is up to the compiler engineer to decide which registers to use and which variables to in which manner the parameters have to be passed to the function, right? From one function to another. So the one disadvantage of this type of parameter passing is, now if I have to access any of the parameters that have been passed A, B, or C, I should access the stack memory, right? It's a memory location. So instead what I can do is I can pass these parameters in registers, right? I can try to map registers like there are like 16 registers, right? So I can map say register EBX, ECX, EDX, something like that, three registers. I can write values of A, B, and C and place it in those registers EBX, ECX, and EDX. And instead of pushing it onto the stack, my function 1, I can emit the instructions. The compiler can emit instructions in such a way that instead of using EBP plus offset to access these parameters that have been passed, I can access directly the registers EBX, ECX, and EDX, which is significantly faster when compared to accessing your stack memory location, right? So this everything is with respect to the compiler engineer, but usually most of the compiler engineers will follow this sort of standard when coming to x86 bit ISA, because when you write C code, right, it's not always the case that your C code will always be executing within that same language itself. You will be accessing other languages functions also. Like for example, you can have like Java code and it will be interacting with some C libraries, and it will interact with some Python AI ML libraries. So all these languages should sort of interact properly with each other, and for this the call-in convention should be somewhat standardized, or at least a majority of them should follow this call-in convention, so that your at runtime when you execute the code, it doesn't break when you're passing parameters. So if each function or if each language sort of like um, it, it sort of uh, changes the way in which it looks at the parameters or returns a value, right? It sort of leads to chaos, and it doesn't lead to good um, like a smooth coding environment, right? Uh, you will be facing lots of errors at runtime, and your code might break also. And if you want to interface with some other language or something, it will be an issue. So this is what the standard call-in convention of x86 32-bit ISA looks. Now for 64-bit ISA or 16-bit ISA or some other different ISA like ARM or RISC-V, the call-in convention will change um, based on it. So by call-in convention, I mean the ISA itself will sort of specify a call-in convention which is sort of optimized for that ISA. So for example, here we saw that there were two registers EBP and ESP which point to the top and end of the stack frame, right? Start and beginning of the active stack frame. And we noticed that the push and pop instructions in x86 ISA implicitly act upon the ESP register which points to the top of the stack frame. So whenever I want to pop some element from the stack, it pops that element and updates the ESP register. If I want to push some element, it updates the ESP register. So the x86 ISA, the processor which implements that ISA, treats the ESP register in a special way, right? So the call-in convention which is provided by the ISA, which is mentioned by the ISA, sort of specifies like a proper way of like a standard way of calling different functions and how to pass parameters, but those can be tweaked by the language, the compiler engineers who build that specific language to focus on their to get some extra performance increase or something, right? So here for example, as I mentioned, right, so instead of passing parameters via the stack memory, they can pass it via registers also. But the only thing they should keep in mind is once they deviate from the call-in convention which is present in the ISA, which is used by the ISA, right? It sort of makes it difficult for some other language to interface with this language. So they should take those steps to sort of like document those changes what they have made in that call-in convention, so that when some other language tries to interface with this language having a different call-in convention, you should sort of document these changes so that everyone stays on the same page. Right. So we looked at parameter passing and return value, but one specific aspect we sort of overlooked at is when we take the main function. So let me create a new frame. So when we so initially if we are having stack frame 1 which is at the main function, okay, and this is where my EBP is present, okay, and this is where the ESP is present, top of the stack. Now when it invokes function 1, right, we mentioned that so we mentioned stack frame 1 and then it will be stack frame 2 and it will be the main function, and this will be fun1, and we mentioned that it will be ESP over here and EBP over here, right? And once it returns back, and once it returns back, it will again be the same, that is the main function, which is stack frame 1, and then this will be ESP and then EBP. So this will be main function. This is when main calls fun1, right? And this will be return to main, right? When it returns back to main. Right. So in this, right, if you notice that the EBP value, the register of EBP and ESP registers have different values at different points or at different time intervals. So when it main is executing, it will be having some value. Say here it was having 0x1000, and here it is having 0x900. So now it will be having 0x900, and here it will be having 0x800, and now again it will be having 0x1000 and 0x900. So EBP register and ESP register has different values based on which function is active, right? But you should note that point that the registers in x86 are sort of fixed, as in like there's just one register which is EBP register, right? You don't have like two registers, EBP1 and EBP2, nothing like that, right? You don't have like multiple duplicate copies of the same register. There's just one register called EBP, one register ESP, right? And the register is sort of the physical value where this register is being stored, right? So if you take your physical hardware, there will be EBP register and ESP register, and there's just one location in the register. Okay, so now when we mention that right, so now when main is executing, it will be having 0x1000, and this will be having 0x900. And in case 2, when this is case 1, this is step 2, when function 1 gets invoked, this will be overwritten with 0x900, and this will be overwritten with 0x800. And when third step, when it returns back, this will again be overwritten with 0x1000, and this will be overwritten with 0x900. Right. So now all this overwriting is happening. So when between step 2 and step 3, right? So when fun1 is executing, it is at 1000 and 900. But when it returns back, how does the processor know, or how do we know that it's not at 1000? Sorry, it's at 0x900 and 800. How does the processor know that the values should be overwritten by this value 0x1000 and 0x900? So how does the processor know? So I have sort of changed my EBP and ESP registers, right? How does the processor know that when I return back from function 1 to main function, the previous values in EBP and ESP should be restored back, right? Should be restored back into the registers, that is 0x1000 and 0x900. How does the processor know? So what happens when one function calls another function is, my EBP and ESP registers are sort of copied in the stack frame. The original copies of original values of EBP and ESP are copied into the stack frame, right? Before I create a new stack frame, the EBP and ESP registers are copied into the stack frame, right? And once so when main calls function 1, right? The old values of EBP and ESP, that is 1000 and 900, are copied into the stack frame, and when function 1 returns back to main function, right, the old values from the stack frame is popped from the stack and is loaded back into the registers EBP and ESP. So the stack frame not only stores the local variables and the parameters which are being passed, but also stores the old copies of the original values of EBP and ESP of the caller function. So the caller function stack frame, that is 1900, the start and end of the caller's stack frame, is stored within the stack memory itself, right? It's pushed onto the stack frame before you invoke function 1 and allocate a new stack frame. And so that on deallocation, when you return back to the main function, you populate the EBP and ESP registers with the stack frame boundary values corresponding to the main function, that is 1900. Okay. So this is another, this is also sort of part of the call-in convention, because this storing of EBP and ESP registers. So now say you have a call chain where you have like function 1 now calls function 2 and function 2 calls function 3, like that, right? So each time when you call a new function, the previous function's stack boundaries, that is the EBP and ESP registers, are pushed onto the stack, so that when it returns back and resumes execution in the caller function, that corresponding stack frame should be active. So active as in the EBP and ESP registers should be having that corresponding stack frames boundary, the end and the start and end of that stack frame should be pointed by that EBP and ESP registers. So those values are pushed and popped, sort of like copied into the memory and then restored back based on the function call chain, right? So when it calls a new function, the caller's value of the EBP and ESP is um, stored into the stack frame, and it overwrites the registers with the new stack frame, whatever gets allocated with that new value. And when it returns back, when it deallocates the stack frame, it restores the caller's EBP and ESP values into the registers. Okay, so this is also a functionality of the call-in convention, and we looked at all the aspects as in parameter passing, the return variables, and um, returning variables, and how does EBP and ESP registers, even though it's just like one register in the hardware, how does it properly track all the currently active functions, right? Which stack frame is active, how does it track, and how does it restore back properly the caller's stack frame boundaries when the function returns back to the caller function, right? So this we looked into. The last thing that we have to look into is what happens, how does the processor know to which instruction it should resume execution. So what we mean by that is, let me create a frame. So what I mean by that is, say if I have the function main. Say you have the function main, okay, and it has it calls fun1 ABC, and it returns, fun1 returns back a result, right? And this result, what it does, it prints the result, say printf sum equal to percentage %t, right? So what now when you look at the execution, there will be how it will look in assembly is you will have your main function, okay, and there will be set of instructions which does something, and then what it will do is it will be pushing the values, push C, push B, push A, okay. So it will be pushing C, B and A in the reverse direction, right? So A, B, C is being passed means in the reverse direction it will push the parameters, and then what it will do is it will also call the function 1. It calls function 1, right? Now what happens? The execution moves to function 1, and the assembly code of function 1, what it will do is it will have some instructions, right? It will compute the sum, and before computing the sum everything, it sort of stores the EBP and ESP into the stack frame, so that when it returns back to main function it restores back. It restores back EBP and ESP on return, right? But and once function 1 returns back, it should resume execution over here. So basically when it returns back, it resumes execution over here, which calls the printf function, okay. So before that what it should do is it should sort of get the local variables, right? So r equal to rax register, right? So whatever return value is present in the rax, the sum of abc, whatever it is, it's stored in the local variable r, and it calls printf function, okay, by passing the local variable r as a parameter. But one thing which is unanswered is how does the processor know that after executing fun1, when I return, it should it should start at this instruction specifically wherever the local wherever it places this, right? Calling r equal to rax, like copying the return value. How does the processor know that it should resume execution in the main function at that specific instruction? So why not the processor start from main function again restart? That's wrong. It cannot start from here, it cannot start from here. These are all wrong. How does the processor know exactly that it should start from this position r equal to rax, right? This information is also stored in your stack frame, okay. So what happens is your call instruction semantics is something like this: call some address, right? Some function wherever that function is present, that address we should specify in the call instruction, right? The call instruction, what it does is it pushes the next instruction address into the stack frame and resumes and continues execution, at the address. So basically what happens is when I invoke this call fun1, say it is present at 0x900, and we have the next instruction at 0x910, okay, this r equal to rax, and fun1 is present at address 0x800, okay, and I have the call address as 0x800, means what the um, call instruction will do is it will say, it will look at the call instruction, it will say, okay, I'm going to call some address 0x800. So basically the execution, so the instruction pointer, the execution should jump from location this 0x900, right? It should jump from 0x900 to 0x800, okay. But before jumping the control flow, before it jumps to 0x800, it will push the value of the address of the immediate next instruction, that is 0x910, onto the stack frame. So if we have the main functions stack frame over here, and we have the variables, local variables c, b and a also pushed onto the stack frame, okay, and the parameters c, b and a, and after this what it will do is it will push the instruction after the immediately after the call function. So that instruction is where I should return back when I return from the function fun1. When it has to resume execution in the main function, you resume execution immediately, the instruction following that call instruction, right? You resume execution over there. So that instructions address, you push it on your stack frame, that is 0x910, and then what you do is you transfer control to function 1, and function 1, it will allocate a new stack frame. It will uh, store the ESP and EBP registers, right? All those things it will do. Okay, and now after fun1 finishes execution, and when it is time to return back, right, when it's time to return back, it uses a instruction called as return instruction. So here return instruction, it doesn't take any operand, right? It doesn't take any operand. Notice that it doesn't take any operand. What it does is, the function 1, first it deallocates the stack frame, deallocate stack frame, okay, and restores ESP and EBP, the main functions. With respect to the main function, ESP and EBP registers, it restores back, and then what it does, it executes this instruction called return. So at the time when it restores back the ESP and EBP, my ESP will basically be pointing to this location 0x910. So this is where the ESP would be pointing to at this step when it has restored back the main functions ESP and EBP. Okay, and EBP would be somewhere over here when it is restored back. Okay, now the function 1, it will execute a return instruction. Basically it means the function 1 has finished execution, and after finishing execution it will deallocate its stack frame, thereby deleting all its local variables, and after deleting its local variables it should return back control to the main function. And how does it return back control? It basically restores the ESP and EBP registers with respect to that main function's value. It restores back that value into those registers, and when it restores that value, my ESP now points to the value at which was there at the start of function 1's execution, before it got it allocated any new stack frame. At that point what my ESP was having, that value, it will be restored back, and EBP will pointing to the start of main function stack frame. And finally the execution should resume execution at this instruction r equal to rax, which is immediately following that call instruction in the main function, right? So now the function 1 executes a special instruction called ret instruction, return instruction. And what this return instruction does is, it does the opposite of the call instruction. So call, basically what it does is it pushes the next instruction address into the stack frame, okay, and it increments the stack pointer. Like when we do a push operation, it not increments, it decrements, right? It decrements the stack pointer, it decrements the stack pointer, and it continues execution at the address 800. So the return instruction does the opposite. What it does is, it does something like, it from the stack pops from the stack, okay, it pops from the stack into the instruction pointer and resumes execution from that value. from that value. So basically my ESP immediately before the return instruction, it will be pointing to the top of the stack, where the top memory location is having the value 0x910, which is nothing but this instruction R equal to RAX, right? And when I do a return instruction, the logic of return instruction, let instruction, is whatever is at the top of the stack, it will pop that value from the stack, right? The ESP will move to this location now. It will pop that value from the stack and place that value into the instruction pointer, right? And instruction found at that address location 0x19, whatever that value which is popped from the stack, the instruction found at that address is the next instruction to execute. So basically, from the function 1 fun1 function, when it returns back, it resumes execution at the instruction R equal to RAX. Okay, so we use the special ret instruction. So this is how functions sort of the processor sort of identifies which instruction to resume execution on returning back from a function. And now say when I invoke like a chain of functions, like fun1 invokes fun2, and which invokes fun3, and which invokes fun4. Basically what happens is, each invocation you store the return address, right, onto the stack frame. So return address as in this immediate instruction following that call instruction in the callers function. What's the address of that instruction? That's the return address. So over here 0x910 is the return address. So you store the return address on the stack each time you invoke a new function, right? And that happens as part of the call instruction itself. And when you use the return instruction, the return address on that stack location, right? The stack pointer is pointing to that specific slot which contains the return address. And when you use the return instruction, it pops the value of that return address from the stack into the instruction register and executes that instruction found at that address. And it basically resumes execution in the callers function. Okay, so this is what happens when one function calls another function. Main function calls fun1 or any function, right? So this is what happens. So to sum up what we saw in this lecture, right? To sum up what we saw in this lecture, to basically to have a quick recap, right? So when main calls function 1, okay, so we have something called what steps are involved, right? So what happens at the caller's side, what happens at the callee's side. Okay, so first what happens at the caller's side, what it does, it pushes the parameters. So push itself is onto the stack location only, pushes onto the stack, right? And second, what it does, it calls the function, and calls the function, actually it stores the return address on the stack. And at the callee side, what happens is, it stores EBP and EBP value only, right? So it stores the EBP only. ESP it need not store, right? That's like redundant information. ESP always points to the top of the stack. So ESP is not a must. If we know one, we can derive the other also. Okay. So it stores the EBP, and followed by that, the fourth thing what it does is, it allocates local variables, whatever fun1 is using, onto a new stack frame, and after finishing execution, right, it deallocates the local variables. All the accesses will be via EBP or ESP, right? And it deallocates the local variables. So by deallocating, what we mean is it basically changes the ESP. So the top of the stack, if I just add some bytes, right? So basically it grows upwards then. So whatever is present below that, it's sort of getting deallocated, right? So it deallocates the stack, all the local variables, that is adding offset positive to ESP. Okay, and finally what it does is after it deallocates the stack frame, restores EBP value, which is the main function's EBP value. It restores back to the EBP register, and once it does, it return instruction. So once it does this, it does the return instruction, and return instruction, it will basically resume execution at the return address which is stored on the stack. It will pop that address and resume execution from there, and that should basically, if any return value is passed, it should take copy of the return value which is present in the register EAX. Right, so this is what happens in your when we call one function to another. So if you look at the C code, it will be like simple, right? Okay, you call a function, but underneath all these steps occur. You push all the parameters onto the stack, and you call a function. You should place some information with respect to where it should resume execution in the caller function when the control returns back to main function, and afterwards, in order to when the control returns back to main function, I should also identify that active stack frame, right? So for that, I should store the current copy of the EBP register onto the stack frame, so that when it returns back, I should know where the stack frame is. For that, I should store at a later state so that I can restore it back, and then I should allocate a new stack frame for fun1's local variables, right? And once that is done, I should deallocate the local variables, that is add some offset to the ESP, and then I should restore the original EBP value which was present initially at the start of fun1's execution, and then I should do the return instruction which takes the return address which the call instruction pushed onto the stack and returns back to the main function, and in the main function it should do something with the return value which is present in the EAX register. So one step which we missed in between is before deallocating the local variables. So over here, if any return value should be passed, right, it should populate EAX with return value. So this should also happen in between, right? So these are all the steps that occurs when one function calls another function and when it returns back to that function. And this sort of happens, sort of like mostly happens on every function call, but this is the standard, but there are variations in these also. For example, if I don't pass any parameters, then step 1 is not present. If I don't pass any return values back, then step 8 is not present. Okay, and in compilers there is an option like omit a frame pointer register. So basically, instead of using reserving this EBP register, since the number of registers are sort of constant and they are high in demand, the compiler engineers might give an option to use this EBP register for some other purpose instead of pointing to the start of the stack frame. And for that, what they do is they have this option called omit frame pointer. So we'll look at these options in the next lecture. So when that is used, your EBP register won't be used at all. So you won't be having this third step, storing EBP, right? And the size of the stack frame will also differ based on the number of local variables you used. So this is the whole concept of call-in convention. That is, we take from one function, it calls another function, we pass the parameters, store some context onto the uh, stack frame on the stack region, and enter function 1 execution, and when it returns back we resume execution at the proper location, restore back that context and all those stuff. Okay. So in next week lectures, we will look at a debugging tool called GDB, and using the GDB tool, we will inspect the call stack frame. We will look at runtime, how say we'll take a sample program and we'll look at how when one function calls another function, the stack frame gets allocated, how does the local variables are populated into the stack frame, and what happens, how the registers value get changed and all those stuff. We will look using the debugging tool, right, which will be an interesting study actually. So thanks everyone for attending the lecture. Let's meet, if there are no queries, then let's meet in the next week lecture, Friday 7 p.m. Thank you everyone. See you.